Hi, we're going to look at the chapter of current of electricity. Right, this chapter is before direct current, so students must understand the concepts under this chapter before you can proceed to the chapter of direct current. Right, in the chapter of direct current, the first thing we have to look is the concept of current. Right, current I is defined as the rate of flow of charge, right? Where I equals to Q over T. Q is quantity of charge. Quantity of charge, where the unit is coulomb, C. And Q is Ne, where N is the number of electrons, and E is the charge of an electron. And E carries a value of 1.6 times 10 negative 19 coulomb. Right? So therefore, I equals to Q over T, Q equals to IT, okay? And IT is equals to NE. So therefore, N over T is equals to I over E. N over T is known as the rate of flow of electron. It means it is the number of electrons flow per unit time, okay, or per second, right? So that is the definition of current and how is it related to N over T, right? Now the next thing we're going to look at is the derivation of the formula I equals to NEVA, right? Where N is the number of electron per unit volume, or it is also known as electron So it is known as electron density, which carries the unit of per meter cube. E is the charge of an electron. Okay. V is known as drift speed. And A is the cross-sectional area. So if you have a conductor and the length of the conductor is L, the cross-sectional area of the conductor is A, current is flowing through the conductor, I, and the electron flows in the opposite direction, or it is drifting with the speed v, right? So we want to find out the relationship between I, V, A, EVA, and N, electron density, right? So from the definition, right? From the definition of current, I equals to Q over T, where this is equals to NE over T. So I equals to NE over T, right? So that is equation 1. Drift speed is the distance over time where it is moving through the conductor of length L, so L over T. So therefore, T equals to L over V. So we now substitute equation 2 into equation 1. So I equals to NE LV. So we have NE V over L. So this becomes equation 3. Okay, so the volume of the conductor V equals to A over L. Sorry, V equals to AL. L equals to V over A. So this is equation 4. So we substitute equation 4 into equation 3. So I equals to NEV E over A. So NEVA over V, where N over V, this is the number of electrons, and V is the volume. So by definition, okay, we look at it, N is the number of electron per unit volume. All right, to ensure that the students are not confused, so I'm going to put a bar here to differentiate that this is the number of electrons per unit volume, okay, whereas this N without the bar is just the number of electrons, okay. So therefore, N bar, which is the number of electrons per unit volume, is N over V, right? So therefore, this equation becomes N bar EVA, right? So this is the derivation for the equation I equals to NVA. Okay, the next concept we're going to look at is potential difference, V, right? So let's look at the definition. The definition of potential difference is the electrical energy dissipated per unit charge, okay, flowing between 2 points of a closed circuit. So what does this mean is that if you have a battery, right, and this battery has an EMF of E, and you have a resistor R, so the potential difference across this fixed resistor is V. So according to this definition, is the electrical charge dissipated, okay, by the fixed resistor per unit charge. So what is the difference between potential difference and EMF that we will see after we discuss about potential difference, resistance, and so on. So by definition, potential difference is energy per unit charge. Okay, the unit is joule per coulomb, or simply volts. All right, this is the definition. Okay, just for notes, many students think that the definition or the formula V equals to R is what is used to define the potential difference. This is wrong, right? This formula is used to define the resistance V over I. Okay, so resistance R is defined as the ratio of potential difference to the current. So R equals to V over I, okay? And the unit is ohms. Okay, right. So that is the defining equation for resistance. So that brings us to Ohm's law. Okay, Ohm's law states that the current flowing in a metallic conductor is proportional to the potential difference applied across it, provided that the physical properties such as temperature, length, okay, and etc. are constant. Okay, so I proportional to V, right? So we plot a graph of I versus V, we get a straight line graph. Okay, the gradient is the change of I over the change of V, right? Which is not equals to the resistance, but it is equals to the reciprocal of the resistance. Okay, so that's what it means, right? However, if you look at the definition of the resistance, is the ratio of potential difference over I. It doesn't say it's the change of potential difference over the current. So if you have example, a non-ohmic conductor. So this is an ohmic conductor because it obeys Ohm's law. So for a non-ohmic conductor, example something like this, how do we take the resistance? So we can't take the gradient. So resistance at a particular point, resistance at a point is equals to, okay, let's say V star, I star. So resistance at that particular point is V star over I star. Okay, because the resistance is changing at different point, okay, when the current and the voltage is changing. Okay, let's look at the what we call as current I, voltage V, characteristic for various conductors. Okay, so it's basically IV graphs for various conductors. So if you have a typical metallic conductor which obeys Ohm's law, so we know that it's a straight line. But what if you have, for example, the graph which looks like this, IV, I versus V. Okay, so this is for a filament. Sorry, this is for thermistor. So this is the symbol for thermistor. And this is for filament of a light bulb. Okay, so here the resistance is increasing. Okay, the resistance is increasing because the temperature is increasing. The reason because the filament of a light bulb is made of a coil of wire, and this coil of wire is inside a light bulb. And the resistance of the coil of wire need to increase because you need to heat up the gas inside the light bulb as the temperature increases. Okay, basically when the resistance increases, the temperature increases, and this will help to heat up the gas inside the light bulb, which illumination occurs. All right, so that's how the reason this resistance increase according to temperature. Whereas in thermistor, okay, this is the resistance and this is the temperature. So it is the other way around. As the temperature increase, resistance drop. So here the resistance drop, okay, as the temperature is dropping. Okay, so that's the concept of IV graph. Okay, the other one is semiconductor. Okay, how does a semiconductor look like? So the semiconductor looks like this, the graph. This is the IV graph. Okay, so you have a sharp increase of current at a particular voltage, right? And there's a large, meaning that the resistance is almost infinite, or sometimes it can also go beyond than that. Okay, because here you have what we call as a reverse bias, meaning diode, which is an example of a semiconductor, may not conduct the current or may not let the current to pass, whereas this is a forward bias, right, where the diode allows the current to flow, right? So this is a symbol of diode. Okay. Okay, let's continue more about the resistor. So resistance of a conductor depends on, number one, length of a conductor. Number two, cross-sectional area, A, and this is the length. And number three, depends on the resistivity, rho, meaning the type of material. So this can be related by the equation resistance rho L over A. So rho is the resistivity, L is the length, A is the cross-sectional area. So resistivity is AR over L. So A is meter squared, resistance is ohm, length is meter. So we can cancel this. So the unit of resistivity is ohm meters. So this shows that the resistance of a conductor proportional to the length. The longer is the conductor, the resistance will increase, and it depends on the cross-sectional area of the conductor or the wire. So that means thinner wire will have higher resistance, thicker wire will have lower resistance. Okay, in other words, A equals to pi V squared over 4. So meaning the resistance is inversely proportional to the diameter squared. Okay. Okay, next we look at electrical power, and electrical energy. So electrical power and electrical energy. So from the equation, okay, of potential difference, V equals to energy over charge. So rearrange the equation, we have E equals to VQ, and current equals to Q over T, Q equals to IT. So therefore we substitute this equation into here. So VIT, right? So this is equation 1, right? VIT. Okay. And since V equals to IR, we substitute into the first equation. So E equals to I R I T, so it's I squared RT, right? Or I equals to V over R, we substitute in the first equation, equals to V E R T, so we have V squared R times T. So these are the different equation for electrical energy. So for electrical power, right, power P is defined as the rate of energy dissipated. So electrical energy, I'm going to use VIT over T. Hence, we have P equals to IV. Okay, so from this equation, we have P equals to I squared R. So P equals to IV. Okay, so we know that V equals to IR. So hence we have I squared R. Okay, or P equals to V squared R. So how do we get this equation? I equals to V over R, right? From the equation V equals to R. And then we substitute into P equals to IV. So we have V over R times V. So we have V squared over R. Okay, so this is another equation for electrical power. Okay, and we can use this equation, right? P equals to IV to define or alternate definition for potential difference. So from equals to IV, V equals to P over I. So this is the alternate definition for potential difference. So the definition, right? So potential difference V between 2 points in a circuit or across a conductor is defined as the rate of dissipation of electrical power per unit current I. Right? So this is an alternate definition for potential difference. Okay, next we're going to look at the concept of EMF, which is electromotive force and internal resistance. Okay, is denoted by the symbol small r. Okay, so let's say you're given a circuit. Okay, this is a battery which has an EMF of E, and you have an internal resistance of R, okay, and this is connected to a external resistance R. Right, so this external resistance will have a potential difference of V, and the battery, right? So normally this is how a circuit with a battery of EMF E and the internal resistance is given. So the current is I. So the concept of EMF is basically you have energy input, which is this is by the battery or the power source, right? So in this case is E, which stands for EMF, and then you have the energy output. So in this case is the energy output is through the resistor. Okay, so that's V. Okay, and we also have energy lost, okay, through the internal resistance. Resistance R. So I'm going to put this as VL. So according to principle of conservation of energy, so energy input okay, which is by the battery, is equals to energy output V plus the energy loss by the internal resistance VL. So E equals to V plus VL. Okay. So how does this equation came about? Okay, how does this equation came about? Energy input is I E T, because we have learned about electrical energy. E equals to IVT, this is electrical energy. So I is the current through the circuit passing through the battery E in a particular time E. IVT, the same current is passing through the resistor R, plus IVLT. So this is the voltage loss through the internal resistance. So I'm going to put VL. So the same current passing through at the same time. Hence, you have E equals to V plus VL. Okay. In other words, the EMF can be also written something like this, right out, right? Because the current is passing through the internal resistance. So example, if the EMF across this, say it is about 3.00 volts, okay? Let's say you have a voltmeter across these, and the voltmeter gives out a reading of 2.0 3.97. So therefore, 3.00 is the EMF of the battery, okay? And IR is the voltage across the resistance R, which is 2.97, plus 0.03 is the loss of electrical power, okay? Electrical power or electrical energy. So this is the concept of EMF. So what is the difference between EMF and potential difference? All right. So if you look at this particular case, EMF is the input power, okay? Input power. That means the power which is delivered by the battery. And you have output power, which we can consider this as a useful output power. And we have a power loss, okay? So what is the definition, the basic definition of EMF? So the definition of EMF is non-electrical energy transformed into electrical energy per unit charge. So meaning that for a battery, for a chemical battery, the non-electric energy in this case is the chemical energy, which is transformed into electrical energy, because you need energy to move the charge in the circuit. If you take example, other type of source of electrical power, example, solar cell. So solar cell, the non-electric energy will be a solar energy, which is converted or transformed into electrical energy. Whereas potential difference is defined as electrical energy transformed into other form of energy per unit charge. So if you now connect the battery to a, say, heating element. So this is a heating element, or if you connect a circuit to a light bulb, a filament light bulb. Okay. So what is happening is that the EMF of the battery is converting its chemical energy into electrical energy. And this energy is used by the charge to move around, okay, where the heating element now converts that electrical energy into, in this case, thermal energy, right? Or in this case, the electric energy being utilized by the light bulb, and it is converting that electrical energy into light or other form of energy like heat, right? So that is the difference between EMF and a potential difference, right? Okay, what is the graph related to this formula? Okay, we're going to look at the graph. So E equals to V plus IR, okay, or IR plus I small r. So I'm going to use this particular equation to show the graph. So from here, V equals to E minus IR, rearranging the equation, so IR plus E. And compared to Y equals to mx plus c. So we have, if we plot a graph of V versus I, we get a negative graph. And this gives us the EMF, the y-intercept, right? And the internal resistance will be the gradient. Right, so that is how we relate this equation to the graph, right? So this ends my explanation on current of electricity, right? So the next chapter will be direct current. Thank you.